On polynomials. Polynomials, in particular, we're going to talk about how to graph a polynomial. Now, we already did this. We did quadratics. We graphed quadratics. And how we graph quadratics is we found our two zeros, and then we just looked at the leading coefficient, and we said if it's positive, it opens up. It's a nice smiley face. And if it was negative, it would open down. We're going to do the same thing, but we're going to do ones that are bigger degrees, like third degree, fourth degree, 21st degree. We'll be able to do a 21st degree if it'd be a lot of work, but we could actually do it without using our calculator. So first of all, polynomial. We've seen polynomials before. They're just a string of leading coefficients and x's to powers. And we always take the biggest power, and that's going to be the degree of our function. So if I had x cubed plus x squared plus 3x, it's going to be a degree of 3 because that is the biggest power that x is taken to. Now, when we're graphing polynomial functions, we have to remember two things. A graph of a polynomial function is continuous. That means there's no holes, there's no gaps, there's no breaks in it. So our graphs are going to be continuous when we do our sketches. So that is no breaks, no holes, no gaps. The second thing we're going to do when we're doing sketches of this is a polynomial is a smooth graph. And what I mean by smooth is, it makes like gentle terms. We don't ever have like jagged pieces when we're graphing a quadratic. When we picture a quadratic, it's a nice U shape, or upside down U, I was actually doing, or a nice U shape. So there's only round turns. So everything's going to be nice and smooth when we're drawing it. Nice curves going down like this. There's no jagged, like the absolute value function. That's a jagged function. It makes a V. There's no V's. It's either we're talking about U's or upside down U's. So that's what we're going to think about when we're sketching these. Now, when we sketched a quadratic, we looked at our leading coefficient to tell us what happens at the ends. Either they both go up or they both go down. We're going to do the same thing. We're going to attach something to it. So this is going to be called the leading coefficient test. It's a little misleading. We are going to look at the leading coefficient, but we're also going to look at the degree of our polynomial. So we have to know the degree and whether a leading coefficient is positive or negative, and it actually tells us what happens at the ends of our graphs. So the first thing, if f is an odd degree, so I'm talking like x cubed, x to the fifth, x to the seventh, anything odd, even x to the first follows this, which is just a straight line. So if f is odd degree, and our a sub n is bigger than 0, in other words, your leading coefficient is positive, what's going to happen is the graph will fall to the left and rise to the right. All right, so once again, if it's odd degree, it is going to fall to the left and rise to the right. Now, just a quick example of this. Remember, we don't really know what happens in between. So this would be just a sample of what a graph might look like. That graph right there is odd with a positive coefficient, a leading coefficient. And that is because, once again, it will fall to the left and rise to the right. I'm going to attach something else to this. Our right-hand bound. An easy way to say this is y goes to infinity as x goes to infinity. Because x's are left and right, so as I go right, my graph goes up. And this is how you'd say it. Y goes to infinity, or our graph goes up, as our x values go to infinity, or our graph goes this direction. That means our left-hand bound would be something like y goes to negative infinity, as x goes to negative infinity. All right, once again, that is odd and positive. I can just look at that graph and know it's odd and a positive leading coefficient. Our next one's still odd, but in this case, our leading coefficient is going to be negative. All that's going to do is it's going to take our two arms and it's going to flip them. All right, odd makes the graph rise to the left and fall to the right. So an example of that one would just be opposite direction ends. We would now have y goes to infinity as x goes to negative infinity. And the other end, we're going to have y goes to negative infinity as x goes to infinity. These are odd. I think the big thing to remember about odd is they go opposite directions, right? One arm goes positive, one arm goes negative. And the way I kind of remember this has a positive leading coefficient. Think about a straight line. If like 2x minus 1, that's a positive slope, so it's going uphill. So if you have a positive leading coefficient, it would have positive slope, so it would go up. If you have a negative leading coefficient, think of it as negative slope. And that's how negative slope works. Negative 2x minus 1 goes downhill. So that negative coefficient creates kind of that negative slope, so it's going to go downhill. So if you just think about a line, leading coefficient is positive, it goes uphill. If it's negative, it goes downhill. That's how you know your two end behaviors of odds. Remember, if you're not sure what to do, boil it down to the most basic of odds. Our basic odd is just x to the first. It's just a line. If your end behavior works a certain way for a line, it'll work the same way for a cubic, a fifth degree, a seventh degree. All right, so these are odd. Let's go to even. Even's a little less fun because we've already done even. We've done all these. We did it with the quadratic. What works for a quadratic is going to work for any higher degree even. So I'm talking x to the fourth, x to the sixth. That is, if it's even and our leading coefficient is positive, they both go up. Just like a quadratic. Quadratic makes a smiley face. A fourth degree might not be smiley face, but they're still going to go both up. So I'm going to do something that's not quite a quadratic. My example is going to look something like, maybe like a W. It's even because both ends go up. It's a polynomial. There's no gaps or anything in here. It's a nice smooth thing. So it's a polynomial that's even and has a positive leading coefficient because both arms go up, just like a quadratic. Now, if they're both negative, or if our leading coefficient is negative, then they're both going to go down. So maybe we do an example kind of like, maybe we'll do a fun one. That's super fun, right? No, I wouldn't do that much. That gets a bit tedious. Something like that. But you can definitely make graphs that just keep going up and down for a long time. Once again, leading coefficient's negative, it's even. It has to go both down. It has to. There's no other way to change it around. Every single even function, or even degree, that has a negative coefficient, both ends are going to go down. All right, so without knowing anything else about polynomials, we're just going to graph the end behavior of these two, or these four functions. All right, so we have y equals 2x cubed minus x squared plus 9. So the two areas I'm looking for the degree. Well, that's odd. And then I'm looking for my leading coefficient. Well, my leading coefficient's bigger than, so my a sub n is bigger than 0. So we have two things. It's odd degree. Odd degree means the arms go up or down. Right? There's one of these. And then we also said our leading coefficient, a sub n, is bigger than 0. Well, a sub n being bigger than 0 means it has kind of that positive slope. So we're going to start down, and we'll end going up. So just knowing that two things, I know my graph's going to look something like that. I'm not sure what happens in between yet, but I do know it's going to start here, and it's going to end there because of our leading coefficient test. All right, our next one is 6x to the fourth. Once again, I'm just looking for what's the highest degree of this. Well, that's 4, which means it is even. That 6 right there is my leading coefficient. That's my a sub n. is bigger than 0. So this function is even degree. And our a sub n, or our leading coefficient, is positive. Our leading coefficient is positive. Well, even should be a little easier because we already did it with quadratic. We said with the quadratic, it's even, it makes a smiley face. Well, same thing for any even, is both of our arms are going to be up. It's like, yay, we're even and we're positive.
Yeah, we like winded.
There's like a dance.
Logan does that dance all the time.
Yeah, he was doing it in class.
I always die.
Wait, so what is it? I don't remember what it is.
I don't remember it either.
Was Will Carroll
There's, like,
going
more than
absolutely
going
nuts?
No,
Who wasn't?
no.
Are we gonna get Miss Kessler?
There's something wrong.
What was that?
Are we gonna get Miss Kessler?
Oh, it's an online video.
Bring in Logan.
She taught us it.
Oh, did she?
Really well.
Oh, I bet. All right, anywho. All right, we are going to have y equals 5x minus 7x to the 4th. I'm just going to change it around to negative 7x fourths, so my biggest power is out front, plus 5x. And I'm not doing that so much to realize it's even, because most of us are really good at getting even. But sometimes, even though you say it's even, you put your 5 as your leading coefficient. That's like a big mistake that people make, is when they keep it in this form, they realize it's even, but all of a sudden they take this 5 as leading coefficient. So I do rewrite it every single time, so I can recognize, yes, it is even. And our a sub n is less than 0, because our a sub n is at negative 7. Even, less than 7, we are going to go down. All right, last one. We have odd. Degree. And our a sub n is less than 0 because that is our negative 12. Our negative 12 is less than 0. Once again, I'm picturing negative 12, that's a negative slope. A line with negative slope goes like this. So my end behavior is going to kind of look like negative line. It's going to go up here and down here. Any questions on any one of those? So once again, our leading coefficient is just not our leading coefficient. We have to look for the degree and the leading coefficient. All right, 0 is a polynomial. We need to figure out what happens in between. What happens in between those two arrows? So when we are dealing with a polynomial, f, of degree n, we already talked about in the last section that n is the number of possible real zeros. So if I have x to the 5th, I have 5 possible real zeros. The only thing I'm adding on to this is the graph has at most n minus 1 turning points. A turning point is a relative min or max. So maybe an example of that might be that. This right here would be a turning point. And this right here would be a turning point. So just basically where it changes direction, where it goes from positive to negative slope. That's what I mean by turning point. So if I have x to the 5th, I have 5 possible zeros, and I have 4 possible places it changes directions. Not really the coolest thing to memorize because you're going to actually figure out whether it's a turning point or not down here. So just knowing this, I'm more concerned about finding all my real zeros, making sure I had all that stuff taken care of. And this will kind of get taken care of down here. So you won't, most of the time you're not going to go, okay, do I have 3 turning points? No. Okay, I got to go back and find another turn. You will know all your turning points right here. And that's going to be based upon our multiplicity of our zeros. So what we're doing is we're finding zeros, and we're figuring out what the multiplicity of that 0 is. And remember my example, I think my example from the multiplicity one was like if I have x minus 3 to the 4th power, I'd have x equals 4 is one of my zeros, or 3. I forgot what did I say, x minus 3. Okay, x equals 3 is one of my zeros, but it has multiplicity of 4. Multiplicity is key at knowing what happens at those zeros. We know at the very least it reaches that 0. When we did quadratics, if I found 2 zeros, it went through both of those zeros. However, if my quadratic only had 1 0, it would just touch that 0, turn right back, and go back up. That's when our vertex was right on our x-axis. Well, it's not a coincidence, and we're going to figure out how to tell that right here. So we have a factor x minus a to the kth power, where k is bigger than 1, yields a repeated 0, where we have x equals a of multiplicity k. And in fact, k can actually equal 1, and it's going to still work out. We'll see that in just a second. So if k is odd, the graph crosses the x-axis at x equals a. So once again, odd crosses. Odd crosses. That's important to know. What example did I do here? I did kind of what I just said. I did y equals x minus 3 to the 3rd. That means I have a 0 at x equals 3, but it has a multiplicity of 3. So I'm going to note this 3 and say that is odd. The multiplicity of this one is odd. But we do know that it's going to cross at, so we have a 0 at x equals 3. So it's odd, so it crosses, and it crosses at 3. So just knowing that, and I kind of gave weird ratio of room here. So I'm going to actually put this graph kind of more up here. And I'll put an arrow to it. So if I zoomed in, if I took this graph and I graphed in my calculator and I zoomed in right at x equals 3. So 1, 2, 3. That 2. What you would see is this graph would actually cut through right at 3. All right, it would go right through at that 0. So that is this example. Odd multiplicity, it means it cuts right through or goes through. Even means it's tangent. It just touches it and then goes back down. It doesn't actually go through at that 0. So it bounces off of it. So even, it's tangent. My example of this one was, what if we had y equals x minus 2 squared? Well, that's even multiplicity, and we have x equals 2 for our 0. So our graph of this one would be, if you zoom right in at x equals 2, oh, you do not want to do anything, do you? There we go. So if I zoom right in at 2, this graph would look something like this. It would bounce right off that 0. It would hit that 0 and bounce right off. Odd goes through, even bounces off. Well, if we now know what happens at the zeros, and we know how the graph starts and ends, we can use all that to come up with a nice sketch of what any polynomial looks like, given that I can find the zeros. Sometimes the zeros aren't easy to find. Like, picture an x to the 21st power one. That would be really hard to find the zeros. But say you could find the zeros. Now we know the graphs. So let's go ahead and practice. Let's do 2 of these for examples. The first thing you're going to do is you're going to do a leading coefficient test. You're going to do this every single time. You're going to do a leading coefficient test, because on the test for this thing, if I ask you to do a rough sketch and you just know the end behaviors, at least you can get some points. All right? It's probably the easiest thing to learn is our leading coefficient. Leading coefficient, we actually are looking for the leading coefficient and the degree of the polynomial. So our degree on this one is 3, so it's an odd degree. And our leading coefficient, a sub n, is bigger than 0. Because it really is that 1 that's out front there. All right, it's bigger than 1. So it's odd degree, and it's positive. Odd degree has the arms. Positive, I'm thinking positive slope. Picture a line that has positive slope. Positive slope would look something like this. So our arms are going to do that. Yep, Charlie. We're going to do something like that. Positive slope. Honestly, that's how I think of it. Positive slope. If you know the dance, you can do the tans on the test. I don't care. All right, so now I know the end behavior. I just have to know what happens in between. And for that, we're going to find our zeros. So the next thing is find the 0 and look for how many times they're repeated. So I'm going to have 0 equals, well, I'm going to start off by just factoring an x out of everything, because x comes out of all of it. So we're going to have x times x squared plus 2x minus 3. Well, let's hope this is factorable. Even if it's not factorable, I can still find the zeros, right? If you can't factor something, you just put in the quadratic formula. You put it in, you complete the square. Don't end here. Once you get to x squared, you can find your zeros regardless whether it's factorable or not. So we're going to have x times an x. Well, I need a positive 2. I need a negative 3. Let's do positive 3, negative 1. Hey, on the test, a lot of us factored something that was unfactorable. We just disregarded going backwards to make sure it works. I always check. I always go plus 3 times negative 3 does equal a negative 3. Plus 3 minus 1 does give me my positive 2. It worked. It's factorable. We now have 3 zeros. We have x equals 0, x equals negative 3, x equals 1. But it's not enough for me just to find the x's. I need to know their multiplicity. I need to know their multiplicity. Well, the good thing about these is they're all to the first power. X to the first, x plus 3 to the first, x minus 1 to the first. So all of them are odd. All of our zeros have an odd multiplicity. Multiplicity of 1, 1, 1, all are odd. So let's rehash what odd means again. Oh, odd means it crosses at those points. So at every one of those zeros, the graph is going to go whoosh right through it. All right, and it's the only place that they're going to reach those zeros. So to make this graph, we're just going to make an xy plane. We don't know any of the y values, but we do know x values. So we're not going to label our y with numbers. All I'm going to do is I'm going to label my x with numbers. And I need to get from negative 3 to 1. So let's go 1, 2, 3. We'll say that's my negative 3. We'll go 1, 2, 3. That's positive 3. And now I'm going to mark my zeros. I'm just going to place a mark for all my zeros. We have 1 at x equals 0. We have 1 at x equals negative 3. We have 1 at x equals 1. I know it starts down low, because that's what we said down here. So this line is going to start here, and it's going to cross at negative 3, because we have a negative 3, and it's odd, so it's going to cross there. So we're going to have something like this. Now what I'm thinking as I draw this, it needs to get back down here. Because at the very least, this graph is going to hit all of these, at least bounce off or go straight through. So I do have to make it back down to that 0. And as I'm making my way to that 0, I'm asking myself, does it bounce off or does it cut through? Because it's only 2 possibilities. Well, I look at my x equals 0, multiplicity 1. Odd multiplicity means it's going to cut right through. So it's going to cut right through, and it's got to make it back up to that last 0. That last 0 is x equals 1. Multiplicity is 1. That's odd, so it's going to cut right through. And now I'm going to go back to what I thought my end behavior was supposed to be. That matches. I am pretty certain I did everything right. It is really hard to come up with your end behavior, come up with all your zeros, and make it bounce off one of these the wrong direction and still get the graph right. Because picture this. Let's say I bounced off this one. I'd have to bounce off this one and then come through, so I have to get 2 of them wrong to even make it look right. All right, so just make sure you compare your sketch with what you thought the end behavior was, and most of the time you have it correct then. All right, last one. I'm going to start us off, and then you're going to finish it, because it is a slightly harder factoring one. So we have x to the 4th minus 200x squared plus 10,000. Let's do our leading coefficient test first. So I'm saying, well, this is even, right? So we have an even degree. Our leading coefficient is 1, but 1's bigger than 0. That's positive, so a sub n is bigger than 0. Once again, that is that number that's out here. And so a really rough sketch, super rough, because I just know the end behavior is it's even, it's positive, both arms are going up. So like, yeah, I'm positive and even. It must be the best one. All right, so that's what my end behavior should look like. Let's go ahead and factor this guy to find our zeros. So we're going to find our zeros next. My hint is always, if I have x to the 4th, x squared, and just a number, it's factorable just like a binomial times a binomial. And what we're going to have is a binomial times a binomial where I have x squared in front on both of them. Because x squared plus x squared, or times x squared, is going to be x to the 4th. And if I do my outside inside, I would have some number times x squared. All right, inside, I need to make a positive 1,000, but I need to come up with a negative 200. So I'm thinking, well, 100 times 100 equals 10,000. Negative 100 times negative 100 also is a positive 1,000, but negative 100 plus negative 100 is also going to be negative 200. All right, there's a couple ways to do this one. We could end right here. I'm going to go one step further, because if I solve for this 0, I would have, can you kind of picture it'd be x squared equals 100, and the multiplicity would be 2, right? You guys see what I'm saying? Let's do it. Let's do it. I'll do one more step for you. So I have this guy right here. We have x squared minus 100 equals, let's go a different route. I'm going to go a different route. So I'm going to say 0 equals, I'm going to actually notice that these are a difference of squares. So I could rewrite this as x minus 10 times x plus 10. So I'm just taking all of this, realizing it's a perfect square, and writing it like that. Because that is x squared minus 10 squared. Well, the same thing's going to happen for the next one. We are going to have x minus 10 times x plus 10. That is, this guy is a perfect square, so I can rewrite it as that. If you don't believe me, distribute it. Make sure it works. All right, but then I'm going to notice something. I'm going to notice that I have x minus 10 and another x minus 10. That's x minus 10 times x minus 10. An easier way to write that, almost a bless you. It's like you stopped it. An easier way to write that would be x minus 10 squared. Well, we have the same thing with x plus 10. I have 2 of those. So we can do x plus 10 squared. All right, that matches the other one we did a little better. So what I want you to do is, okay, let's go ahead and finish this. It looks like everyone got it. So let's refrain from talking. I'm just going to talk through just in case you weren't sure. So let's make our graph. Now, I'm making the graph, right? I don't need to make a whole bunch of lines until I get to 10. I'm making this. I'm making the values. So if I know I have to go from negative 10 to positive 10, what might be a good idea is maybe count by 5s. Negative 10, positive 10, because that's as far as I need to go. Now I know I have a 0 at negative 10. I know I have a 0 at 10, so I'm going to mark those. I also know that at the end of the day, I need it to look like that. So let's start from left to right. So I know it needs to start like this. And I know it needs to reach that 0, that negative 10. What happens at negative 10? Does that bounce off or does that go right through? It bounces. How do I know it bounces? Because it's even. So let's look here. So in fact, both of them are even because I have that 2. I have that 2. These are both even. So both are going to be tangent. That means it bounces off. So when I get down to the first 0, it bounces. It's got to make its way back to the other one, bounce off, go up, and that's what our graph looks like. Or to have graphed this. Let me see if I can bring up my graph. You're going to notice pretty quick, I got the wrong graph in there. So we have x to the 4th minus 200x squared.
You have 20x squared.
I do have 20x squared. It doesn't. Thank you. I think I would have missed that, and then we would have the wrong graph, and I would have got angry and smashed stuff.
That would have made class much more interesting.
Right?
We should do that today.
All right, so if I just hit zoom standard, does that look like the graph we drew? Here's why. Think about what zoom standard does. Zoom standard zooms into negative 10 to 10. That's right where our zeros are. So what's actually happening is I'm zooming in right here. Somewhere up here is that U-shaped. Somewhere up there is my U-shape. So we have a couple options. We can try zoom fit. Some of our calculators will work, some of them won't. In fact, it will depend on which time you try whether it works or not too. I can almost see my W, right? I can see kind of that middle of the W. So let's go to my window. So I'm going to go to my window. And I'm going to look at my window, and it's still zoomed in at from negative 10 to 10. I need to widen my x-axis. So I'm going to plug in negative 20 to a positive 20. No, 22 will be fine. And I'll hit graph. There's our W. So just because you're not getting the graph you thought you were going to get is probably because you're zoomed in the wrong place. You have to use a combination of zoom fit and changing your x and y values. All right, you have to change your window sizes to look at these graphs. So if you're on the test and you're checking one of these, just make sure you don't change your whole answer because your graph doesn't quite look right. Make sure you change your look around your graph to make sure you're looking at the right section of it. Otherwise, that's